Hello and welcome to Brunei Math Club. The goal of this video is to prove that for a square matrix A of order n, these three conditions are equivalent. That is, A is invertible, the rank of A is n, and A can be decomposed into the product of a finite number of elementary matrices. Okay, let's start. First, let's review some important properties of invertible matrices and inverse matrices. A is said to be invertible if there exists some matrix X, say, such that AX is equal to XA is equal to the identity matrix. And this X is called the inverse matrix of A, or just inverse of A. And such inverse is unique. So there are no two or more distinct inverses for a given matrix. So we write the inverse as A inverse. And finally, if A and B are both invertible matrices of order n, then their product, AB, is also invertible. And the inverse of the product is the product of inverses, but the order of the product is reversed. These facts are used throughout this video. Okay, here's the first theorem of this video. We first consider elementary matrices of order n, Pij, Pi of C, and Pij of A. These matrices are used for elementary row operations or elementary column operations, as we have learned in previous videos. We show that these elementary matrices are invertible or regular, and their inverses are given as this. First, let's look at this one. So Pij, for example, if used for elementary row operations, swaps the row I and the row j. And if we swap them again, then we recover the original matrix. So that means the inverse operation is achieved by the same operation. Therefore, the inverse of Pij is Pij itself. And next, consider this one, Pij of C that multiplies the row I by the constant C if multiplied from the left. So if we want to recover the original matrix, all we need to do is to multiply the same row by the inverse of this constant, 1 over C. That is this. So that's the inverse matrix of Pij of C. And for Pij of A, this operation, if multiplied from the left, adds A times row j to row I. So if we want to recover the original matrix, we multiply row j by negative A and add that to the modified row I. So the inverse of Pij of A is Pij of negative A. So that's basically all there is for proving this theorem, but let's look at the proof a little bit more closely. So here it is. So if we multiply Pij by itself, then we get this. So we have Pij here, the same matrices, and this is Ji element and this is Ij element. So if we multiply them, so let's take this row I and multiply with column j. So 0 times 0 is 0, 1 times 1 is 1. So the II element becomes 1. So row I, column j, 0 times 1 is 0, 1 times 0 is 0. So the Ij element becomes 0. And similar for this one and this one. And as a result, we get this diagonal matrix with all the diagonals being 1. That is the identity matrix. So since Pij is the same as Pij, of course, so we can see that Pij is the inverse of itself. Okay, next let's look at this product. So pi of c times pi of c inverse. So we have this matrix and this matrix. So this is a diagonal matrix, so all the off-diagonal elements are 0. So if we take this row, the row I and the column I, if we multiply them, we get 1. And if we swap the order, this becomes C inverse and this becomes C, and we still get the same result, the identity matrix. Therefore, the inverse of pi of C is equal to pi of C inverse. And finally, let's look at this product, Pij of A times Pij of negative A. So we have this matrix, and this is the ij element, and this is the ij element. So let's take the ith row and the jth column. So 1 times negative A is negative A, and A times 1 is A. So the result is 0. For everything else, the diagonal becomes 1, and off diagonals become 0. So the result is the identity matrix. Now, if we swap the order, this becomes negative A, this becomes A, and we still get the same result, the identity matrix. Therefore, the inverse of Pij of A is Pij of negative A. And we are done. Now, before proving our main result, let us prove this lemma first. Let A be a square matrix of order n such that all its nth row elements are 0. If that's the case, then this matrix A is not invertible. So what this means is this. So if we have a square matrix, its nth row, the last row, is all 0. So if that's the case, then A cannot be invertible. Let's prove it. First, let X be an arbitrary square matrix of order n. So it can be any matrix of order n. And we consider the product between A and X, and in particular, its nn element, which can be calculated as this. So A and J times xjn, and J runs from 1 to n. But since we are assuming that the matrix A has this form, so the nth row elements are all 0, so this is always 0. Therefore, the sum is equal to 0. So the nn element of AX is 0. So it cannot be equal to, this matrix cannot be equal to the identity matrix, because of course the nn element of II, the identity matrix, is 1. So no matrix X can satisfy this equality. Therefore, the inverse of A cannot exist. And we are done. Now we can prove our final goal, which characterizes the structure of invertible matrices. Let A be a square matrix of order n, then these three conditions are equivalent. Let me state it again. A is invertible if and only if the rank of A is n, if and only if A can be decomposed into the product of a finite number of elementary matrices. So these Q1, Q2, and so on up to Qs, they are all elementary matrices. So whether we say A is invertible, the rank of A is n, or A can be decomposed into this form, they all indicate A is invertible. So the strategy of the proof is this. We first prove 1 implies 2, and then we prove 2 implies 3, and finally we prove 3 implies 1. Then we should be done, right? So let's start. So 1 implies 2. To prove this, we use proving by contradiction. So we assume A is invertible, so that's the premise, and the rank of A is not n. So from that, we draw a contradiction. But the rank of A is always less than or equal to n, so the size of the matrix. So we assuming the rank A is not equal to n implies that the rank of A is strictly less than n. Now, let's define B as the product between P and A, where this P, a new matrix, is the product of a finite number of elementary matrices, P1, P2, up to Ps. As we have learned before, multiplying an elementary matrix from the left, like this, means an elementary row operation. And by a series of elementary row operations, we can always transform the matrix A into its reduced echelon form. So this B is the reduced echelon form, and each of these elementary matrices is invertible, as we have proved. And the product of invertible matrices is also invertible. Therefore, this P is invertible. And we are assuming A is invertible. The matrix B is also invertible. But since B is the reduced echelon form, then it has this form. 1, 1, and so on, and 0, 0. And the rank of A is less than n, so in particular, at least this last row, the nth row, contains only zeros. Because the rank of a matrix is defined by the number of rows that contain non-zero elements in the reduced echelon form or echelon form. Since we're assuming the rank of A is less than n, at least this last row must contain only zeros. But that means matrix B is not invertible according to the lemma we have just proved. So B is invertible and B is not invertible, which is a contradiction. Therefore, we have proved condition 1 implies condition 2. And next, let's prove 2 implies 3. So suppose the rank of A is n, which is the condition 2. And again, let B, the matrix B, be defined as P times A, where P is the product of a finite number of elementary matrices, and B is in the reduced echelon form, just like we did here. Then, since the rank of A is n, the reduced echelon form must be equal to the identity matrix, because A is a square matrix. And we know that this P is invertible. So multiplying this equation, both sides of this equation, by P inverse from the left, we have P inverse times PA. So this is the left-hand side, P inverse times PA, but this is equal to the identity matrix. So the left-hand side becomes A. And the right-hand side is P inverse times I, which is P inverse. So we have A is equal to P inverse. But P is equal to this. So the inverse of a product is the product of inverses, where the order of product is reversed. So if we have defined P in this way, then P inverse becomes this. But we have proved in the first theorem that the inverse of an elementary matrix is again an elementary matrix. So each of these inverses is an elementary matrix. Therefore, A is expressed as a product of elementary matrices, which was what we wanted to prove, and we are done. We are done proving this statement. Okay, lastly, we prove the condition 3 implies condition 1. So suppose A can be decomposed into the product of a finite number of elementary matrices. So Q1, Q2, and so on up to Qs, they are assumed to be elementary matrices. Then we know that elementary matrices are invertible, and the product of invertible matrices are invertible. Therefore, this whole thing is invertible. That means A is invertible. And we are done. That's all for this video. See you later. Bye. Thanks for watching. If you like this video, please hit the like button and subscribe to this channel. See you next time. Bye.